Last meeting, we finished resultant of concurrent force systems, and then we started with the resultant of parallel force systems. We answered up to this number, right? Now, we just continue answering our problem set. So let's move on to number 2. Once again, ready your calculator for faster solving. So number 2, the beam AB in the figure supports a load which varies on intensity or an intensity of 220 Newton per meter to 890 Newton per meter. Calculate the magnitude and position of the resultant load. So we're looking again for two things, magnitude and position. And we have this loading diagram. So it starts off at 220 Newton per meter up to 890 Newton per meter. Let's solve. So we have a load diagram, and I've discussed previously that whenever we have load diagrams, one of the first things to do is to convert it to a point load or its resultant load. So as you can see, this does not have a regular shape. It's it's a combination of two shapes. So you can still divide your load diagram into two parts, okay, so that you have your common shapes. So the way to divide this is to divide it into a rectangle and then into a triangle. So we have two separate load diagrams, meaning we have to solve for 2-point loads. So let me mark that out. So first we have this, a rectangle. Let's consider that. Okay. So this rectangle, I'll add a color to it so that's easier to see. Violet. We know that the position of the resultant of a rectangular load diagram is right at its center. So it's somewhere here. Okay. So we can call that F1. Okay. The point load of your rectangular load diagram. And then we have another one, your triangle. So let's have a triangle. Choose a color just so to distinguish our figures. Okay. And then the position of the resultant or point load of a triangular load diagram is 1/3 from the higher end. So this is the higher end, about 1/3 of that is somewhere here. So let's call that F2. Now let's compute. Recall that the resultant is just equal to the area of your forces. So let's start with F1. Rectangle, so it's just base times height. Okay. This is our height, your 220 Newton per meter. So just multiply that 220 by 6. You get 1320. Now don't forget your direction. All of these load diagrams are downwards. So since downward it's negative 220 times 6, you'll get negative 1320. Do the same thing for F2. It's a triangle, so that's 1/2 base times height. So 1/2 your load, 890, times length, which is again 6. Please compute what's the answer here. Sorry, oh, my bad. This entire height is 890. I'm only concerned with this height, right? But I'm not supposed to multiply by 890. Instead, it's 890 minus this, which is equal to 220. So 890 minus 220 times 6. Okay. Correct, it's negative 2010. So correct, Michelle and Francisco. So Legado and Leon. Okay. Once again, take a closer look at your figure. Height of your triangle is just this, not this. So it's negative 2010. Don't forget the negative signs, since it's downward. Okay. The first thing that we're looking for once again is magnitude of the resultant. All of these are just downward lobes. So computing the magnitude is easy. That's just summation of forces. Okay, in this case, they're all downwards, so that's just F1, negative F1, and we already have this. So negative 1320 minus 2010. What's the final answer? Very good. It's negative 3,330. Correct, Kurt and Naomi. So De La Cruz and Munoz. Negative 3,330. Unit, don't forget, our unit of force is newtons. Now, this negative sign does not denote incorrect assumption. We didn't assume anything. It's already shown. So this just denotes its direction. So you can also write it this way, 3,330 Newton downward. Okay, so that's the first part. Next, you want to know the position. So to do this, we're going to use the concept of moment and then choose a reference point. Okay, so let's say my reference point is A. So you're going to take moment at A. And then next, you're going to guess. And this is where you assume the position of your resultant. I'm going to assume it's somewhere to the right of A. Again, usually it's in between your forces, but not all the time. There's cases wherein it's outside. So this is just guessing, making an assumption this is my resultant R. Okay? So take moment about A, and that is just equal to RD. Remember our new equation for resultant of parallel forces. Create our equation, summation of moment at A. So there's, let's start with F1. Okay, rotate F1 about A. That's clockwise, so positive F1. Okay, by the way, similar to what we did with resultant, this negative sign again just denotes direction. So if you're going to use this in your computation, use the absolute value. Okay, so this is also equal to 1320 downward, and this is 2010 downward. Let me adjust. Okay. Once again, F1, rotate about A, that's clockwise, therefore positive F1 multiplied by perpendicular distance to A. This is in the middle of your rectangular load, therefore it's half the base. Therefore, this length is just 3. Okay, so F1 times 3. Do the same for F2. This is F2, rotate about A. Once again, that's clockwise, so plus F2. Get the distance. So this distance right here is 1/3 your base, right? So this is 1/3 times 6. I want to get this distance since we're taking A as my reference point. Therefore, this distance is 2/3 of 6. Okay, I'm going to write that. So the distance is 2/3 of 6. Okay, there's no other forces. Again, we're just talking about resultant here. So we'll equate that to your resultant. This is my resultant. Rotate that about A. Clockwise, therefore positive R, and then B. and this is B. Let me place in our values. Okay. Once again, you're going to use the value only. You're not going to include the sign in this equation. So this is 1320 times 3 plus 2010 times 2/3 of 6 equals R. Again, you're not going to include the sign because the sign was given by your clockwise or counterclockwise analysis. So 3330 D. Please solve. What's D? Correct. It's 3.6. Correct, Kenneth and Luis. Couple Kenneth. So 3.60 positive, therefore correct assumption, it is to the right of A. So specify that here, to the right of A. Once again, if our answer turned out negative, that means we have an incorrect assumption for the location of your R. Okay? So that's number 2. Any questions for number 2? Please answer in the chat. Okay, good. Move on to number 2. Number 3. Okay. Number 3, locate the amount and position of the resultant of the loads acting on the think truss shown. Okay. So same thing with the previous number, just looking for magnitude and position. Let's begin. So magnitude is easy. Just taking the summation, all of the forces are given. So R, again, just summation of forces. So let's include our forces. Let's start from the left side. So we have 890. Okay. Downward. All of them are downward, so all of them are negative. So negative 890, negative 1335, negative 8900, negative 1780, negative 1335, then negative 890. Please compute. What's the answer here? Okay. Yep, it's correct. Negative 15,130. Correct. Kurt, Marilyn, De La Cruz, Palacios. So negative, no, negative 15,130 unit Newton. Again, this just denotes sign. So or 15,130 Newton downward. Okay, so that's R. Now how about position? So once again, position, you're going to use the concept of moment and take a reference point. So as you've noticed, usually I'd like to take the reference point at A. Okay. If there's a reference point mentioned in the question, then you should use that. So far, there's no mention of that. So you can choose wherever you want. Once again, I'll choose A. Now, if we try our method, right, it's just force times distance for moment. If we get to 1335, you'll see that the perpendicular distance of point A is not given. So we need to solve for that first. Okay. So let's solve. Again, let's have this. we need this distance. Okay, let's call that distance x. Now, as you can see, for this small right triangle, we have a right triangle. I'm only given an angle. There's no sides. Now, if I can figure out one of those sides, I can use your trigonometric functions to solve for x. So the next goal is to find a way to solve for one of these sides. Okay? So one way to do that is to look at another right triangle, specifically this one. Okay? Once again, let's try to color that to give you a better look. So this is your violet, the smaller right triangle. And then let's color in this larger right triangle. Let's use blue. Okay. Right. So if you look at this blue triangle, right triangle, you'll see that okay, we have an angle and we have the hypotenuse. So from that, I can solve for these two. And once again, I'm just concerned with the smaller one. So most likely I should solve for this. So let's call that L. Okay. Let's solve for L. Let's create an equation for L. So we have this, we have hypotenuse. We need the adjacent length to your angle. So we'll use cosine. Cosine theta equals adjacent, which is L, again considering the larger right triangle, over hypotenuse, which is 3. So from this, our equation is L equals 3 cosine theta. Next, let's consider your purple right triangle. Okay, so I need this x. I'm given an angle, I'm given now, this L is the hypotenuse, right? So I have hypotenuse, I have angle, I need the adjacent. So once again, we'll choose cosine. So cosine theta equals adjacent, which is x, over hypotenuse, which is now L. Now let's sub in our values. X is just equal to L cosine theta. So 3, L is 3 cosine theta. So 3 cosine and theta is 30. So 3 cosine 30 times cosine 30. Please solve what's x. It's 2.25. I'll just move this. Okay. Now that we have distances, we can move on to solving for its position. So same thing we did earlier, we'll use moment. I took my reference point at A. Oh, wait, point. Recitation. 2.25 for Gian and Colin. Bustos and okay. Meter. Okay, so moment at A equals RD. D is what we want to know. So you can guess again the position of R. Let's say oh, my R is somewhere here. My reference point was A. So this is that distance D. So let's start with MA. Let's start with the left force. 890 passes through A, so ignoring that. Next, 1335. Rotate about A, that's clockwise, therefore positive. 1335, perpendicular distance is X, which is 2.25. Next force, 8,900, rotate about A, clockwise, therefore positive. Perpendicular distance is 3. So plus 8,900 times 3. Next, this rotate about A clockwise, therefore positive. 1780. perpendicular distance, okay, is this. Now, this is symmetrical, okay? Therefore, this 1780 acts half of this 3-meter span. Therefore, this is equal to 1.5, okay? So 3 plus 1.5, that's 4.5, okay? Let's draw that as well. Okay, so this is 1 point, choose a darker color, 1.5. Therefore, perpendicular distance, again, 3 plus 1.5, 4.5. Next, 1335, rotate about A, clockwise, therefore positive, 1335, perpendicular distance. Okay, so now we have this. Okay. Again, it's symmetrical. Therefore, if this is x, this is also x, right? X is equal to 2.25. The entire span is 3. Therefore, the remaining length is just 3 minus 2.25, which is equal to 0.75. So this is 0.75. Therefore, distance of 1335 from A is 3 plus 3 plus 0.75, that's 6.75. And 6.75. And then lastly, we have this 890, rotate about A, once again clockwise, so positive. 890, distance 333, so that's just 9. And let me just make this smaller. Then equate that to our D. Our, solve for that, 15130, wala pa. My guess is this position, rotate about A, once again, that's clockwise. So 15130. Please solve, what's D? Correct, 3.62. Okay, correct, Naomi and Zaira. You also, please. So D is equal to 3.62 meters. Okay. Also positive, therefore, correct assumption. I forgot to write that. So let's specify it is indeed to the right of A. So to the right of A. Was it specified? Okay, no. So you have to write to the right of A. Okay. That's number 3. Any questions for number 3? Please answer in the chat. Okay, great. Now, actually, there's a shortcut to this. I'll show you. So the solution for R is the same. Okay. Now, the next trick, I mentioned earlier, this is symmetrical. The great thing about symmetry is because of that, we can simplify this entire system. Okay. So it's symmetrical for this part only, right? You can simplify all those forces into one. Since they're symmetrical, 890, 890, 1335, 1335, and then 1780 in the middle. I'm gonna take the resultant of all of those forces, and it's gonna act at the center. So therefore, if I take this again, Let me just make a smaller version. Okay, instead of having these forces, we'll just have one force acting here. And it's just the summation of these. Okay? That's 6225, right? 890 plus 1335 plus 1780 plus 1335 plus 890. Okay, sorry, it's 6230. Once again, that's just the summation of all of this. That's 6230. So let's put 6230 here. Then Newton. Resultant is still the same. You can still use this method. But for position, now let's use this. Once again, we're gonna guess where that position is. So I'm gonna guess here. This is my R. Take moment at A. Moment at A equals, and now look, all we have are two forces. So equals RD. Let me zoom in. Okay, so we're starting at A. There's no more force. We'll start at 8900, rotate about A, that's positive, therefore clockwise, therefore positive. 8900 times 3. Next, 6230, rotate about A, clockwise, therefore positive. 6230. And what's the distance? Again, this is at the center. It just divides your 3-meter span in half. Therefore, this is just 1.5. So the distance of 6230 to point A is 4.5. Once again, that's equal to 15130 times D. So please solve. What's D? It's 3.62 again. So correct Rain, Simon, and Eman. Centones, etc. Right. 3.62, positive, correct assumption, it's to the right. To the right. Okay. As you can see, we got the same answer as before, but one solution is shorter than the other. Okay, so this is solution 1. Okay, you can do that. Fix this. Then this is solution 2. I didn't have to solve for x anymore. Okay, so that's the shortcut. If you have a symmetrical system of forces, you can simplify it into a single force by taking the summation and putting it at the center of the resultant of the system of your forces, okay? Not the center of your figure. Okay, so that's method 2. Any questions for method 2? Please answer in the chat. Great, let's move on to number 4. The last question for parallel forces. Okay, 4. The resultant of 3 parallel loads, one is missing in the figure, is 13.6 kilograms acting up at 3 meters to the right of A. Compute the magnitude and position of the missing load. Okay, now so it's reversed. We're given a resultant, we're looking for a missing load. So let's try to indicate our given. We had a resultant. It's 13.6 6 kilograms acting up at 3 meters to the right of A. 3 meters to the right, it's already specified. By the way, this is A. So 3 meters. It's somewhere here, right? Acting up. So this is our resultant. 3 meters to the right. We're looking for a force F. So let's write that this is actually equal to 13.6 kilograms. So R equals 13.6 kg. Right. So to solve for F, since we're given R, we'll just use the equation R equals summation of forces. So now you have to guess the position of F and the direction. So I'm gonna guess, let's choose violet. I'm gonna guess it's upwards. Let's guess it's downward. Since just by inspection, I can see that 27 plus 18 is greater than 13.6. So there must be a downward force to bring that down to 13.6, right? So I'm guessing the third force is downward. So let's call that. Okay, let's create our equation. R is just equal to summation of forces. R 13.6 upwards, therefore positive, equals, let's start with the leftmost force, that's 18, upwards, therefore positive. Next, F is downwards, therefore negative F, and then lastly, upwards 27. From this, please solve what's F. Correct. It's positive 31.4. Positive, therefore correct assumption. So correct Kenneth and Marilyn. De la Cruz Peliosis. Lynn. Kenneth. 31.4. Once again, I assumed it was downward. I had a positive answer, therefore correct. Right. Therefore, it's 31.4 kilograms downward. Okay. Next, position. So as usual, to take position, just take moment about a reference point. Obviously, we'll take it from point A, since that is where our R is referenced, or distance is referenced. So MA equals RD. So let's start again with the leftmost force, 18, rotate about A, that's counterclockwise, therefore negative 18. Distance given, 0.6. Next F, rotate about A, that's clockwise, therefore positive. F, and we're looking for this distance. So let's F times distance D. Let's call that X. So this is distance X. Next, 27, rotate about A, counterclockwise, so negative 27, distance is 3.4 plus 0.6, that's 4 meters. Times 4. There's no other force. So equate that to here, R. So rotate R about A, that's counterclockwise, therefore negative 13.6, and distance is given 3. Please compute what's X. Positive 2.48. Okay. Greg, Zaira, and Luis. Ortiz and Tao. Alright. So 2.48. Positive, therefore correct assumption of position, it's to the right. To the right of A. Okay, that's number 4. Any questions for number 4? Please answer in the chat. Okay, good. And that ends our discussion for resultant of parallel forces.